We will continue working through work, power, and energy, and the concept of work and energy are very much related. Now, energy traditionally defines the ability to do work. If you have no energy, you can't do work. If you have no energy, you can't lift heavy things. We now know that the forces that are able to do work now what we're dealing with is the mechanical energy, which does follow this definition. The energy that is talked about in chemistry, different kind of energy. You're looking at energy stored within bonds of chemicals. Here we're looking at more of a mechanical energy. And therefore the amount of energy is the ability to do work. So if you don't have enough energy to do the work, you're not going to get a full allotment out of it. Also, in physics is the better understanding of us understanding why we cannot have 100% efficiency. Well, one, there's the whole all right, so Newton's second law of motion. So Newton's second law again relates to the net force on an object to its acceleration. There's a relationship between the Werk and Energy theorem as well. So it relates to that, how much work is done on a system to the change in energy of the system. And that's where a little bit of thermodynamics kind of helps us out. And that's where, if we take all of the different energies or the amount of work done by a system and then add them up, it's going to, I think, make life a little bit easier as we look at one of the previous examples, where we looked at all the forces and then just added them up to make life a little bit easier for us and actually see the amount of work done on that system. Because the directional component for the work done on that system isn't necessary at all. The directional component isn't there. It's not necessary. All right, the work energy theorem, which tells us that energy and work are related. Using the constant acceleration equation of v sub f squared is equal to v sub I squared plus 2AD allows us to do an algebraic substitution into the total work equation. There's a bunch of algebra that happens in between there. Okay? Now ultimately this leads us to another equation, and that is the kinetic energy equation of the kinetic energy is equal to 1/2 mass times velocity squared. Now, a lot of times you will see kinetic energy written as either a K or a KE is an alternative method in which it is written. And I've even seen other reference materials to use other letters as well for kinetic energy. That is just an unfortunate side effect, I think, of physicists using different ones to whatever works for them. Like potential energy, I've seen it as U, but then I've also seen it as a capital P, but that doesn't always work. And I think it's just not a nice thing sometimes to students. It would be nice if we had one letter for that's potential energy, just like we have on the periodic table. The letters are they're kind of set in stone. So because the total work done is equal to the change in kinetic energy, that's where we're allowed to make that connection before us. Because ultimately, this is a kinetic energy, final, kinetic energy initially, and the difference between them would be the change in kinetic energy. So it's the total work done on an object is equal to the change in kinetic energy. So the energy can go up and energy can go down. Energy can go left, energy can go right, but usually not all, they're not going up, down, left, and right at the same time. Energy is a scalar quantity. Because kinetic energy and work are related, their labels are also related. Kinetic energy is labeled as the joule and not the bling bling kind. As I mentioned earlier, like work, the standard metric unit is the joule and not the bling bling kind. Oh, my twos didn't square out like they're supposed to. Okay. And as we've mentioned before, kinetic energy is a scalar quantity and therefore does not have direction, even though velocity and acceleration, force, momentum do have a directional component to them. Kinetic energy does not. It is describing the magnitude only. And the reason why we have the label of the joule and not the bling bling kind is by a physicist who is also a brewmaster, James Prescott Joule, or Joule. Now, why do we bring up the idea that he was a brewmaster? Well, because he was a brewmaster, he had access to highly sensitive thermometers. And what he did was a very simple lab that he had kind of a tub of water with a thermometer in there. It had a pulley system that when one thing went down, that in turn would move a paddle wheel inside the water. Okay. So when they dropped it a certain distance, he dropped the mass a certain distance, the paddle wheel moved the water around, increasing the temperature. And therefore he was able to start to make that connection that there was the paddle wheel did work on the water, and that water is increased in temperature, and we're able to actually measure the amount of energy that was transferred to the water. And that kind of gives us that connection to the why is that important? Because he was actually able to measure very small increments of temperature increasing by doing it that way. The mass fell, moved a certain distance over a certain time, and in turn did work on the water. And therefore we get the connection between work and energy. And it is the same connection between work and energy that we use in chemistry when we're dealing with thermochem and the kinetic energy that the objects have, and transferring and tracking the amount of energy that happens on those as well. But this is not chemistry, so therefore thermochem is just a foregone thought from our minds from chemistry years past. Here we're more worried about an object's kinetic energy that it has in a collision, that it has the instant before it hits the ground, before it interacts with another car, to allow us to backtrack certain things and be able to deconstruct crime scenes in those manners as well. Through the process of doing work, energy can move between one world, external world, and the system, and vice versa, from the system to the external world. That just means it's losing it then. The direction that it goes will determine. Then the work is positive and the energy in the system increases. However, if a system does work on the external world, the work is negative. And the energy of the system decreases. Work is transfer of energy by mechanical means. So work needs to be done for energy to be transferred. If I throw a ball, some work had to be done onto that ball over a certain distance for work, for it to have a certain amount of energy, which is calculatable by the velocity squared times the mass. Now we can then with this in all reality, you can almost figure out, okay, how much energy was lost due to friction, and then you can figure out, okay, how far did it go over that time, and you can kind of back calculate maybe with a force of air resistance, if you wanted to dive further into things. So a couple things that we need to make sure that we're aware of in a problem like this. In a 105 gram hockey puck, that is something that we have to convert. So we'll have to make sure that our mass is going to be equal to kilograms, which means that we have to convert our 105 grams into kilograms. If we need the mass. Since it's being done on a sheet of ice, we can go under the impression that that's at 180 degrees. Player exerts a constant 4.5 newtons of force. I would guess that a slap shot would probably have more than that. And over a distance of 150, nope, not even 150 centimeters, be like 15 centimeters. Now we'll resize this. So in a problem like this, we don't have a couple things for us, and we need to have some things, but we can find the amount of work, and that is force times distance. Normally because of the cosine of theta, but we can kind of eliminate that because angle of 0, right? So of a force over that distance, so I don't like using red unless it's wrong. So 4.5 newtons times 0.15. So 4.5 times 0.15 gives us a 0.675 joules, and not the bling bling kind. Now, that's the amount of work done. What's the change? How much work was done? That much. Why can we say that? Because work is equal to the change in kinetic energy. Change in kinetic energy.